Okay, good morning again. So welcome back to our class Control Theory 1. So the topic for the lecture today is about pole zero and stability analysis. The objective of this course is for you to learn how to analyze a system, whether it's stable or not, from transfer function. And there are four main content for this lecture. First, a review of a transfer function, and then I'm going to give a definition of zeros and poles. Then we go to the main point, which is stability analysis. So let me review about transfer function. So, so by the definition, the transfer function is a function described in the complex domain, or we can say Laplace domain. And the relationship between input, output, and transfer function is like this. Let's say you have a transfer function a of s with input say u of s and output h of s. Then the relationship between these three is output equal to transfer function times input. Okay. Or we can say, okay, a transfer function by definition is the ratio between output and input. And transfer function can be represented by a block diagram. Um, so first you have input, and input multiplied by the function in this block, which is called transfer function. Then you have output. Okay. And one thing that you need to know, very important, a transfer function must have degree of denominator larger than that of numerator. Okay. uh, h of s is fractional function described by Laplace variable s. Okay. so let so fractional function means both numerator and denominator are polynomial. Let's say for the numerator, we have degree n. Yes, more of the time they use okay, degree m. Okay, plus in this way, or I think it's better to write this way. Say a0 plus as plus a1, and then a ms power m. And for denominator, you can have b0 plus b1s plus dot dot plus bn s to the n. Yeah, what you have to note is that n must be greater or equal than m. So this is called a proper system. So why n should be at least equal to m? Well, let me give you example of derivative. Yeah, actually, if you have Laplace transform of h dot of t. Yeah, so this equal to s time Laplace transform of h of t and plus no minus f of 0. It's not f but h 0. But okay, let's say this one is 0 for convenient. So if you say, well, if I have input h of t or h of s, fine, and then you have a transfer function s, then you have h dot of s because they represent a derivative. But this time this s time h of s, which is from here, yeah. So h of s times s is h dot of s. So here, do we call this a proper system? No, it's not proper. Why? Let, yeah, it's not proper because let me give you example. Let's say h of t equal to sine of t and plus 3 2. Then h dot of t equal to cosine t. Okay, let's say this is h1 and then h dot 1 equal to cosine t. And if I give you h2 equal to sine t plus 3, then you find h2 dot of t also equal to cosine of t. What does this imply? It implies that if we can measure the output, let's say we measure the output h dot of t, or you can say h dot of s, and here is the derivative. So here is h of t or h of s. Let's say for this system we can measure this part, and from this value we have no way to observe for the input. Okay, no way to observe observe the correct input. Why I say this? Because if the input is this form, the derivative equal to this. We measure this. And if input is something else, yeah, just different by some constant, then the output is still the same. So from the knowledge of this, how can we observe whether the input should be this or should be this, or should be plus any constant c? We don't know. We cannot observe. So it's called not proper system. And you look at here, the degree of numerator greater than degree of denominator. Okay, so degree here is s power 0, here is s power 1, right? Yeah, so s means s power 1 over s power 0. Degree of numerator is greater than degree of denominator. That's not proper. Well, so actually, in practice, you use MATLAB Simulink, and when you use transfer function, you cannot construct a transfer function as like this, but instead you approximate it by transfer function like this. Let's say this 0.04s plus 1. This one, this coefficient must be small enough. Yeah, small enough mean depends on application. So if it's very small compared to this, it means it is just like s over 1. But by this form, we have degree of numerator and degree of, yeah, we have the same degree of numerator and degree of denominator. Is there any question? And let me give another example to find a transfer function. Oh, well, let me say this. Let me recall the transfer function before. So where do we get that transfer function? So transfer function h of s equal to a0 plus a1s plus dot 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 plus a m s to the m over b0 plus b1s plus dot 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 plus bns to the n. Yeah, where do we get this transfer function from? Um, yeah, like I showed you earlier, that the definition of transfer function is the ratio of output h of s over input u of s. Then you can rewrite this as b. Yeah, I can write h of s times b0 plus b1 of s plus bn s to the n equal to u of s a0 plus a1s plus dot 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 plus ams to the m. So uh, distribute all these factor, yeah, all this term, then using the inverse Laplace transform. Well, let me give, yeah, all initial condition are 0. I just want to emphasize that, so I don't need to write down here, so that I can easily use the Laplace inverse to be h of, yeah, b0 h of t plus b1 h, no, 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 no. Wait. Yeah, h of t should be here. Then b1 h dot of t plus dot dot plus bn h. Um, how do I write this? Do I write something like this? Yeah, or maybe it's easier to write this way. So here should be Bn d an order over the t to the n, and here it's of t equal to, yeah, similarly for this one, you have a0 u of t. So u here is in for the not step function. uh, yeah, sometimes most of the time we use u as a step function, but here just u is general input. A plus a1 d over dt u of t plus dot 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 plus am d over dt, yeah, dt all of power right? Yeah. And u of t here. Okay. um well, so we can see that if n is greater than or equal than m, it means the differential form of h here has h has more differential form than u. Then it's called proper system. All right, I think that's all for transfer function. Nothing more about it that you need to know, because after then we will discuss about stability or something. So up to this point, are you already familiar with transfer function? If you have any question, please don't hesitate. Okay, no more no question. Lihur, are you okay with this?
Yeah, sure.
Okay. Then the next point is about zeros of a transfer function. So for zero, actually, there are two types of zero. One is finite zeros, another one is infinite zeros. So I'll talk about finite zero first. So let me recall a transfer function h of s equal to a0 plus a1s plus dot 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 plus a s to the m over b0 plus b1s plus dot 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 plus bns to the n. So finite zero means, to find finite zero, you take the numerator equal to zero. This is called numerator, and this one is called denominator. To find finite zero, you take numerator equal to zero. Then because uh, it has degree m and s can be complex number, then to solve this polynomial all equal to zero, you have m set of roots. Okay, So you find s from here. You have s1 equal to, let's just uh, call let's call minus z1. I use minus because no, I use minus z of z1 or z1. Which one is more convenient? Let me see. Um, yeah, minus z1. Okay, it's more convenient. So you have s2 equal to minus z2 dot dot dot, and sm equal to minus zm. Okay, so you have set of roots for this equation. So this is called finite zero. And then an s can be rewritten as, once we know the root of the numerator, we can rewrite as a factor form. Okay, so it is equal to am factor s plus z1 time s plus z2 dot 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 time s plus zm. Okay, so you can see the degree of s is up to m, 1, 2, up to and the coefficient of s up to must be am, right? Here am, here am. So any question so far? I will often use this term. Okay, no question. Then I continue to the next point, about infinite zero. So what is infinite zero? Yeah, actually zero means, yeah, the term zero come from, yeah, the original zero comes from, you set h of s equal to zero. Then for the finite zero, we already say, yeah, n of s over d of s equal to zero. And we already, for the finite zero, we already take n of s equal to zero. Okay, this one finite zero. Now for infinite zero, we can also say d of s go to infinity, right? So this is for infinite zero. Because it's called infinite because it's not exactly zero when d of s go to infinity. Yeah, actually d of s go to infinity, n of s also go to infinity, but because degree of d of s greater than degree of n of s, it's possible that this ratio tend to zero. Okay, yeah, it's possible, because this one has degree n and this one has degree m, and we have n greater than m, I mean greater than or than equal. So in the case of n greater than m, d tend to infinity can make h tend to 0. Okay, Well, I think it's better to say for the finite zero. Um, finite zero, we yeah here finite zero we say it's better to say for finite zero. We say a of s equal to zero, and then we yeah like this. And for infinite zero, we should say a of s approach to zero. Then this approach to zero. Then just take this one, right? Just erase this. Just say d of s tend to infinity, and yeah, where degree of n greater than degree of m. So this one has degree n, this one has degree m. Yeah, of infinite zero exists when n greater than m. Otherwise, it doesn't. I mean, otherwise means n can be equal to m. Yeah, so let's give example to for us to find both finite zero and infinite zero. Let's call a of s equal to s plus 1 over s plus 2 s plus 3. Okay, so finite zero would be s plus 1 equal to 0, then s equal to minus 1. So this is minus z1, which means z1 is 1. And infinite zero, infinite zero, we take limit s go to infinity of h of s, then we can have limit s go to infinity of s over s square, right? Or I can say limit s go to infinity of 1 over s. So here we can see that finally the degree of denominator is 1. Yeah, after we cancel the degree of numerator and denominator, we still have degree 1 of denominator, which means 1 infinite 0. Okay, 1 infinite 0. Yeah, there is only 1 infinite 0. So try to understand and memorize this terminology. Okay, so it's kind of terminology, but later you will learn that this is very useful for you to study uh, controller design for feedback, yeah, for closed loop system. using root locus. So for now, just try to get this terminology. Is there any question, Munivan? Munivan, do you have question? Munivan, are you still here? If you don't answer me, I will put your attendance to 0 again. Because I assume that you are not in the class. Munivan, are you here? I cannot hear you. Okay, I can see your chart. So why don't you talk? Right. Um, Sung Hok, you have any question?
No, teacher. Teacher, can you hear me now?
Yes, I can hear you.
Yes, I have no question yet, teacher. Thank you.
Okay. So the next part is uh, poles of a transfer function. Okay. So what is the definition of poles? Let me recall the transfer function. Oh, yeah. So here is the transfer function, and the definition of poles. Yeah, for pole actually there are only finite poles. Okay, different from zero, right? It has only finite poles. Okay, it has finite poles only. And how to find finite pole? Okay, why is that? Yeah, to find finite pole, we find s such that h of s go to infinity. Okay, then we can have uh, the numerator of s go to 0. Yeah, actually it's just equal to 0. I explain this way just to clarify that it has finite poles only, because if we consider s go to infinity, h cannot go to infinity, right? I mean, if n of s go to infinity, it cannot implies that h of s go to infinity. Why? Because degree of d of s is larger than degree of n of s. Then if we take n of s go to infinity, d also go in go to infinity, which is larger than n of s, then this one will go to 0. So in s of h of transfer function, h of x cannot go to infinity when you take n of s go to infinity. Right, so everything's clear. Then I will just say, well, to find poles, um, yeah, we take this and then we find d of s equal to 0. Then we, s have minus p1, s can equal to minus p2 dot dot dot, or s n. So this one s1, s2, sn equal to minus pn. Okay. Then actually the denominator can be rewritten as, okay, bn s plus p1 time s plus p2 time dot 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 s plus pn. Okay. We have degree n of s, and the coefficient of n to the n, s to the n is bn. Okay, so why zero and poles are important? Well, I explain the importance of pole first. For zero, yeah, later on, because uh, you will see how zero affect to the stability when we analyze the root locus. But yes, the set of roots. Okay, when we choose a particular controller, I mean controller gain, if we increase the gain, then where the set of poles goes, and we can see the effect of zero with that sets. But so now I only explain the importance of poles on the stability. Okay. uh, yeah, so we can start with the stability, which is the next point. And so here, when we say stable, actually it can be mathematically described by exponential conversion. Okay? Again, here I link with the poles with exponential convergence. So let's see a differential equation. You have seen before many times. Say h dot plus h equal to u of t, where u is step. Okay, is step, which means Laplace transform of u is 1 over s. Okay, so using Laplace transform, we have h of s, s times h of s, or h of 0 equal to 0. Yeah, and here is h of s equal to u of s. So I have s plus 1, h of s equal to um, 1 over, oh wait, um, yeah, I want to show the transfer function first. Then we can have a of s over u of s equal to 1 over s plus 1. This is transfer function h of s. And clearly we see that poles equal to minus 1. Okay. Yeah, pole minus p1 equal to minus 1. Maybe I can say s1 equal to minus p1, which is minus 1. Okay. Yes, pole is the value of s that make the denominator 0. And then let's see the solution of this equation. So to find the solution, let's see the step response. Okay, step response of the equation, of the differential equation. Yeah, step response means u of s equal to 1 over s. So I can write down that h of s equal to 1 over s plus 1 times u of s equal to 1 over s times s plus 1. Okay, or equal to 1 over s minus 1 over s plus 1, right? S plus 1 minus s, it becomes 1. Yes. Then using Laplace inverse, we can have h of t equal to 1 minus e to the minus 1 t. Okay, minus 1 here. If I say s plus pole here, p, then p would be, put a p here. Okay, now you can see the relationship between poles and exponential conversion. So you can see that the poles minus p appear here. When t go to infinity, then exponential of minus pt, for this example, it is 1 by the way, minus 1 by the way. Then it goes to 0. This is called exponential conversion. Yes, this term just converge to 0. So this differential equation converge, I mean the solution converge, and the system that is described by this equation is stable. Okay, so when we say stable, we refer to a system, and if we say convergent, we refer to the mathematical, or the mathematical solution of the equation that describe that system. Is there any question, Kumlai?
No, sir.
Okay. Well, yeah, so we call stable. I want to explain another way. Um, so for stable system, yeah, I want to explain another way. So let's say we have is here system, and we inject input. Let's say we design a controller and such that we have a complete system, a feedback system like this. So this just the system can be represented by a differential equation. Just call it ODE, ordinary differential equation. Okay, so here is input u of t, here is output h of t. So we want to control, I mean, we want output h of t just approach to the input. We can call it input or we can call it command. Okay, or we can call it reference, which means for this control system design, we want, okay, we want h of t just approach u of t. So u of t is step like this. What we want is the solution that converge, okay, converge to here. Yeah, for example, if this system is described by the transfer function h of s, which is equal to 1 over s plus 1 that you saw earlier. Um, yeah, we can really have convergence. The exponential term converges to 0. The remaining is just 1, which means h of t just go to 1 like this. Okay. Yeah, here is what I illustrate to understand. Yeah, when we can achieve output approach to what we want, we call this system stable. Okay, stable system. But if the transfer function is h of s equal to 1 over s minus 1, okay, a different case. Let's say this is 1, this is 2. So the red one is 1, the red one is h1. Okay, then um, for the solution of this one, we have h2 of t equal to 1. Should we find it, right? We should find it first. H of s equal to h of s times u of s equal to 1 over, yeah, I try to make black all of this. So h of 2 of s equal to 1 over s minus 1. So h of s, h2 here, h2. So here s minus 1 and 1 over s equal to 1 over s. Here should be minus I made a mistake before. What? Yeah, that's correct. Um, well, here should be minus what? 1 over s minus 1. No. Wait. Maybe like this. Is it correct? s here, and then minus s minus 1. Minus 1 and minus here become plus 1. Yeah, okay, so this is okay. And then what I have is for the Laplace inverse of this one would be h of t equal to exponential of 1t minus 1. Okay, yeah, h2. So h2 here start from minus 1, say minus 1 here, and then when t go to infinity, then h2 of t go to infinity even faster, right? Yeah, even faster, because this one is exponential. So exponential, it's just go like this. Okay, this is h2 of t. So now you can see that for the system, we command u as a step function 1 like this. We want h2 converge to 1, but then h2 just exponentially grow or explode. So this one is unstable. Okay. The red one is stable. Stable exponential conversion. And I have this one 2 times. Oh, divergent, unstable. Really. Here is unstable. Yeah, so actually I already explained unstable system. Okay, when you have divergent, so the exponentially grow like this mean divergent. Any question? So the explanation of both stable and unstable system is are here. Well, if no question, then you can have a break for 15 minutes. So we will restart at 15 past 9.
Thank you, teacher.